Right? Can we start? So this is a summary of the direction which we are going to. So general relativity. Okay. General relativity is a relativistic theory for gravitation. It will generalize Isaac Newton's theory for gravity. We have been discussing last time the fact that Isaac Newton's theory has problems with the axioms, fundamental axioms of special relativity. So this is the new theory which is going to generalize, which is going to replace Isaac Newton's theory of universal gravitation. So this is a relativistic theory of gravitation. Right? And one fundamental, very important ingredient on very fundamental axiom, I would say, of general relativity is the equivalence principle. The EP. Equivalence principle, right? This has usually two versions. The so-called weak equivalence principle and a strong equivalence principle. The weak equivalence principle, WEP, a strong equivalence principle. Usually it's presented like that, usually in books. Let's consider the weak equivalence principle first, right? What is the weak equivalence principle saying? I think it's written down. Inertial mass equals gravitational mass. So the inertial mass of an object is exactly, according to this principle, is exactly equivalent, equal to the so-called gravitational mass. Right. So, what does this mean? What is that? Right. What is the inertial mass? What is gravitational mass? Right. Let us go back to a very old, very fundamental, very basic question in fundamental physics. What is mass? What is the mass of an object? Well, how would you define mass? Somebody knows that? In physics, how do you define mass? Well, in physics you don't really say what things are, what mass is. You should say rather how you measure mass. Okay? This is a mass is a I don't know what it is really, but I know how to measure mass. You understand? When you have a physical quantity, you must be able to tell anyone with which kind of procedure you're going to measure the mass of an object. Right, so if I take this object, this piece of chalk, right, and I ask someone of you, for instance, please go in a laboratory somewhere and measure the mass of this object. What will you do in this laboratory? Metto sulla bilancia. Yes? So this is one way to measure mass. You put it on a scale, right? Bilancia, scale. Scales. And so you measure exactly, what do you measure with a scale? The weight, il peso, the weight, indeed. And from the weight you get a number, and this number is the gravitational mass, mg. But what does this mean from the physical point of view? This means that you are actually speaking about a property of this piece of chalk which responds to gravity. It is a passive response to gravitation. Right? Okay, and you infer from that a number. Is there any other way to measure the mass of this piece of chalk? Without using gravity. Is it possible to measure this piece of chalk in a laboratory, in an ideal laboratory somewhere, and come out of the laboratory with a number, and that number is the mass of this piece of chalk? Right? Yes or no? How about that? Look, I have a table, right? A perfectly frictionless table. No friction. I know this is ideal, but you have to imagine that you are somehow in an ideal laboratory, physics laboratory, and you have an object, like this chalk or something, and you want to measure its mass. Well, if I act with a force F, a known force on that object, what happens? And the object is eventually free to move. Yes, the object accelerates, indeed. Right? And if I somehow measure the acceleration carefully, what happens if I calculate the ratio force over acceleration? What do you get? Mass. But this is inertial mass, because gravity here is not playing any active role in the experiment, because the weight is neutralized by the upward force, the reaction of the table on the object. So there is no gravity there. Effectively, there is gravity. But I mean, when I want to change the state, when you want to change the state of motion of an object, you act with a force on the object. That means that you are exploiting another property of this chalk. This chalk has inertia. It has a tendency that opposes itself to any change of motion. Now, the quantification of that inertial property is called inertial mass. So you will go to your laboratory, ideal laboratory, and you get out there with a number, and I equals. Now, the great fundamental mystery that Einstein was thinking about is that these two numbers are equal. The inertial response, the inertia, the quantization or quantification of inertia of that object, and the way that object reacts passively to the gravitational field, these two numbers are equal. Okay? This is the weak equivalence principle. This is the point. Yeah? Galileo Galilei had already part of the answer to that. I mean, had already an intuition about that. Indeed. What? Again, Galilei. When you drop two objects having different masses from the same height, they fall freely on Earth. Which one is going to fall if there is no friction, if you neglect air resistance and so forth? Which one is going to fall first? That one or that one? So this means that regardless of the mass of that object, they both have the same acceleration, of course, as you know. This is related to that. Because if you think like Aristotle, you might think, or scheme thought, you might be tempted to say, this object has a greater mass, therefore it has a greater weight. Therefore, since force equals mass times acceleration, it should have a bigger acceleration. But then Galileo already understood that not only you have to look at the effect of gravity, the weight of this object is one property, but the other property is inertia. It will undergo a bigger force, but see, there is a bigger inertia as well. And both effects compensate in some sense. But mathematically, this is just like saying, the weight, if you want to use Newton's equation, is mass of the Earth times the gravitational mass, rigorously speaking, over distance squared, and this must be equal to what I wrote here, the inertial mass actually, times the acceleration, gravitational acceleration. And you see that indeed these two properties of bodies are equal, then you can cancel that. And the acceleration depends only on the properties of the planet or the celestial body, whatever you are looking at. Okay? The equivalence principle, and the fact that mi equals always to mg is an axiom of physics. Insisto un po' su questa cosa, so che sono pesante. This is an axiom. What is an axiom? It is a statement that you accept in your theory without demonstration, theoretical demonstration. That means that today there is no fundamental physics theory which explains why this is true. General relativity is constructed assuming that things like this, equivalence between inertia and gravitation, are true. They assume that it is true. And a lot of experiments, very refined experiments in space and so forth, show that this works very well, apparently, to several decimal places. Precision is very high. And this is experimentally verified. But we don't have a sure, well-established physics theory which explains to you very clearly why mi equals to mg. It is axiomatic at this point. But once you assume that, you can deduce many things. Now, the strong equivalence principle is a sort of generalization, or extrapolation of that weak equivalence principle. It says that what happens in an accelerated frame cannot be distinguished with what would happen in an equivalent gravitational field. Why? This is what I tried to explain already last time. Okay, this is just an example. Now I would like to say a bit more about that. Because these simple thought experiments, in German, Albert Einstein called them Gedankenexperiment. Experiment ideal in Pensiero. These are Gedankenexperimenten. In order to explore the consequences of these axioms, and in order to see what this new relativistic theory of gravity is going to possess as properties. So, Albert Einstein is the main one. And he has these Gedankenexperimenten. And these Gedankenexperimenten, they have to do with freely falling objects in a gravitational field. We'll do this in a second while. They have to do with accelerated frames, right? And so we will look first at what happens in linearly accelerated frames. Sistemi di riferimento linearmente accelerati, come questo qua. Linearly accelerated frames, and then I will try to explain to you what happens in rotating frames, rotationally accelerated frames, because you know that uniform rotation is an accelerated motion. So, good. So, one thing to recall yourself, bring yourself to mind that general relativity is general because it tries to generalize the relativity principle of special relativity with respect to inertial reference frames to any reference frame. So accelerated ones too. And Einstein has in his mind that gravity is the bridge. Gravity is a conceptual bridge. Inertial frames. Sorry. This is a bridge that brings you into the country of non-inertial frames. That means accelerated frames of some sort. This is the universe of special relativity. The bridge is gravity. What we call gravity. And this is the world of general relativity. This is Einstein's philosophy at this point, more or less. Yeah? Linearly accelerated frames. Right, let's start with that. So I'm telling you now that everything that happens in a linearly accelerated frame, right, is indistinguishable. You can't make the difference from inside the system, from within this laboratory in rocket spaceship. You cannot tell the difference between this situation and this equivalent situation. So again, let me explain it again and then we go further. So here the point is that you have a system with some observer in there, right? Having an object, a material object for instance, in his hand. He drops freely that object without giving it a kick or anything at all. And he cannot observe anything from the outside. He only observes systems within the frame. And he doesn't know that someone is accelerating a given direction, towards the upward direction. So this object here will move inertially, because if you leave it at rest and there are no forces acting on this ball. If there are no forces, then this object remains in its state of rest by inertia. Okay, so you see that the equivalence principle is very important here. And the lift is moving upwards in space. This person is, of course, moving upwards as well with the lift. So this object here remains at rest from your perspective, from the outside global perspective. But from the perspective of someone who is inside the lift, he sees the object accelerate towards the bottom of the lift, the system. But in reality, it is the bottom of the lift which is accelerating towards the object. Now, if you are close to the great big planet, right? I have to tell many things here. One thing at a time, okay? What we call gravity causes, according to Einstein and according to the equivalence principle we have drawn, exactly the same thing. This object is accelerating down, and if you have a gravitational acceleration close to this planet here, equal to g, and if A is equal to g, right? Then this guy here cannot tell whether he is close to a planet which generates a gravitational field acting on this object, or whether he is in an accelerated system. Yeah? So you can't tell the difference. This is the fundamental difference. Another way in which you can see this is, another example. You can take the object and throw it away in front of you. Yes, sorry.
Ma in quel caso lì, nel primo caso,
sì,
non si sente spinto in giù l'uomo dentro a...
certo, è per quello che le sue gambe, ottima osservazione, quel tipo qua, quella tipa, il tipo qua, che sta nell'ascensore che sta accelerando in là, sente effettivamente qualche un trascinamento, una tendenza che vorrebbe farlo cadere anche lui, i suoi muscoli esercitano una forza per controagire. Ma come fai anche te quando sei qui sulla Terra? Lui a tutti gli effetti sente quello che sente quando è vicino a un pianeta. Esattamente.
Scusi.
Yes.
Sì.
Sì.
Ho capito. Ma la velocità con cui cade l'oggetto è la medesima nei due casi?
Sì. Se l'accelerazione qua, con la quale, scusa, la parte inferiore dell'ascensore, diciamo, accelera verso la palla, allora lui vede la palla avvicinarsi dalla sua prospettiva, se lui rimane rigido, fermo, verso il pavimento, la base, con una determinata accelerazione più che velocità. Okay. Se quell'accelerazione è uguale a quella che viene percepita vicino in un in un campo equivalente gravitazionale, allora è effettivamente la medesima.
Sì, sì, grazie.
Okay. Other questions? Look at this example here now. So it's the same example, but it's more interesting. Einstein says, lift, person, object. Now you throw the object, okay, horizontally. So the object now wants to go in this direction. Once you leave the object by inertia, since there are no other forces here acting on the ball, yes, it will proceed, it will maintain its state of motion, which is rectilinear uniform motion. So it will move uniformly in the horizontal direction. Now, however, he doesn't know that. But someone is conferring a given acceleration in the vertical direction. So again, you see, the lift is accelerating towards the ball, but at the same time, the ball is moving from the left to the right. So you would expect the ball to kick, or to hit the wall on this spot here, horizontal, in the horizontal direction. Instead, you see this situation here. Sorry, I have to do slightly precise drawing here. Now this object has been moving, it starts here, and while the lift is going upward, it moves towards the right. So now it's here, uniformly. But from his perspective, the ball is not there anymore. And you would have expected the ball to hit this spot. You see, it's going downwards. This is of course due to the fact that the bottom of the lift is accelerating towards the ball, and when the ball moves just uniformly here and actually hits the lift there, if the acceleration is big enough. This means that from the inside, what do you see? You don't see the ball here anymore. The ball has not arrived here, but here. So the effective trajectory is curved. And do you know mathematically what kind of curve this is? Roughly? It's a parabola, because you have indeed a rectilinear uniform motion horizontally combined with an accelerated motion vertically. This gives you parabolic motion. And indeed, when I throw something, okay, in a gravitational field, if I do the same thing here on a planet, okay, if I throw an object, if I leave it, how is it going to fall? What is the trajectory of a thrown object in a gravitational field, geometrically? What kind of trajectory is that? Parabolic. Exactly the same. Falls down because of gravity. But you have exactly the same phenomenon from the perspective of the internal observer. There is no way you can tell the difference locally between what happens here and what would happen in a gravitational field. These two things are equivalent. This is the strong equivalence principle at best. No? Clear? Etc., etc., etc. Now this seems rather okay, rather obvious. But now Einstein goes further. And as usual, in his Gedankenexperimenten, he thinks about the propagation of light. And he does exactly the same thing. This is a picture, very simple. You can find thousands of pictures on the web. This is just one. If you have, like there, okay, this, I will try to draw it as best as I can. have a lift. I'll draw the lift. Let's imagine a nice little surprising thing here. Draw the lift in 2, 3 configuration. Lift is moving upwards. Still have the physicist here, greater one. Okay, standing on the floor. And he holds a light source, a laser light source with a very sharp beam, a well-defined beam, for instance. Now, if you are in empty space like this, and you have a light source, light is propagating again from the left to the right in a straight line. So light should hit and illuminate this spot here, i.e. this height here. Should see a light spot here, should see a light spot here. What happens if the acceleration is great enough, of course, because light is moving from the left to the right with the speed of light c, it's always the same constant. So if the acceleration is big enough or great enough, amazingly, from the perspective of an internal observer, what do you see? Light is going from the left to the right at finite speed. The speed of light is very great with respect to our scales. It's still finite speed. So effectively, light is going to hit this spot. So effectively, the observer, what is he going to see? Amazing. He's going to see that light has not been going this way, but this way. You can't escape that conclusion, can you? It's like a ball which moves very fast. I mean, the light ray has a finite speed. So while light is moving horizontally, there is a vertical acceleration of the bottom of the lift towards the light ray, and in the end, the light ray arrives here. From the outside perspective, the light ray is going in a straight line. But from the perspective of a person who is inside the lift, the trajectory of the light ray is bended. You have an actual deflection of light. So the conclusion of Einstein is, if the equivalence principle is true, then gravity must be something that bends light rays. Okay. Gravity must affect the propagation of light itself. Equivalence principle implies that. Yeah? Now, this stuff here is very non-Newtonian, right? Why? In Newton's theory, you know that the gravitational force exists, okay, but it depends on mass, okay, on the masses of the object. Now, has light got a mass? In Newtonian physics, non-relativistic Newtonian physics.
No.
No. So if the mass is zero, you have zero force. So Newtonian gravity should not bend light rays. Right? Yeah. You understand? So light, you can write here. This is just to highlight the difference between Newton's theory and Einstein's theory. In Einstein's theory, gravity is something that affects light rays, the propagation of light. In Newton's theory, gravity should not affect the propagation of light. Why? Because in Newton's theory, the mass of light is zero. Light is pure energy. It's a wave. Of course, naturalmente. You are going to remember, you probably remember that Newton's idea about light was that light was a flux of tiny, fast-moving little particles which have a mass. That's true. But you also know that Newton's theory of light has been demolished, is not valid because of interference and physical optics experiments, which demonstrate that light is a wave, and the essence of a wave is that a wave transfers only energy from one point to another point in space. No matter, no mass. So the mass associated to light in classical electromagnetism, well, is equal to zero. So in Newton's old theory, all of this means that Newtonian gravity should not affect light. And amazingly, Einstein thinks, well, I have to imagine a theory of gravity then that is such that even light is bended by a strong gravitational field. Because of course, you can imagine that because of the great value of the speed of light, this vertical upward acceleration must be great. So the acceleration must be sufficient. Of course, maybe someone of you thinks, hey, wait, stop, hang on. Stop. You say that in an accelerated system, I see light rays bended. You just said that in Newtonian theory of gravity, light should not be bended. Well, isn't this providing a way to establish absolute motion? Because if you still believe, you're a Newtonian believer, if you still believe in Newtonian gravity, you might think, well, if I observe light deflection, this means that I'm not in a gravitational field. And this means that I am really moving and I can establish absolute motion. Yes, you're right, I would say. But, okay, if you want to be coherent with relativity, the problem is that you have special relativity. The problem is that you have E equals mc squared. And although you are saying that light has no mass, it's pure energy, this energy is somehow profoundly equivalent, says Einstein, to a mass. So effectively, if you want somehow to be fundamentally consistent with special relativity and Newton's theory, you try to make this weird sort of meeting, merging, mixing between these two great theories. You have to include this. But if you include this, then a light quanta, a photon, must have an equivalent inertial mass. And by the equivalence principle, this inertial mass is equivalent to a gravitational mass. And so, even in this relativistic, simple, naive, relativistic Newtonian theory, light is bended. So you can't establish absolute motion rigorously. I mean, this is not enough. Okay. Understand? Anyway, the point is that Einstein understands that gravity is going to be a strange thing. Okay? It has to bend light. Even if you know that light rays are just pure energy. So they manifest themselves as pure energy. Ma non è tutto. C'è peggio. Much worse. Dopo facciamo 5 minuti di pausa e andiamo a interrare. Va bene. Now, another consequence, it's not here, or is it here? Gravity affects clocks, and gravity affects frequencies, and gravity creates redshift and blueshift. It's like Doppler effect, but without Doppler effect. It's purely gravitational. So gravitational redshift. The material is already there. It's quite easy to understand actually, this one. But the consequences are very, very profound, very much amazing. Now, imagine you have a lift. Okay. Again, this famous Einstein reference system. And you have a light source again, something which emits light waves. This is the emitter. And up there you have, at the ceiling of the system, you have a receiver. Right? You receive signals. No, okay. If you emit light waves, you emit wavefronts, and you emit wavefronts with a certain frequency in time, and so with a certain wavelength. Okay? Sooner or later, these wavefronts travel upwards. The distance must be always equal. And here, the receiver receives your electromagnetic signals or electromagnetic waves, i.e. light, mostly. And if the frequency here is nu, frequency nu, frequency, or f, in hertz, then the receiver, of course, receives your radiation, emitted radiation, with the same frequency if the whole system is at rest, in the state of rest. So, now you can imagine what happens when the same sort of system is accelerating upwards. Upward acceleration. Because Einstein thinks, again, always the same stuff, right? What happens in an accelerated frame is equivalent to what would happen in an equivalent gravitational field. If the equivalence principle is true, if you don't want absolute motion even for accelerated frames. The prize of today are these strange consequences, of course. So what happens? You can see it already there, roughly. non è molto difficile intuire, cioè it's not very difficult to grasp a feeling of what is going to happen. You emit, for instance, one wave every second, so 1 hertz here. One wave front, say, every second. So the frequency, roughly speaking, is 1 hertz in 1 wave. So this is what would happen here. If you have 1 hertz here, you have 1 hertz here. It means every second this receiver is going to receive 1 wavefront. Now the emitter is emitting his wavefront. The first one, and the first one is traveling upwards at the constant speed of light, finite speed of light, and it's moving upwards. But now you have to imagine that this frame has a given acceleration in the vertical direction. This means that the receiver will receive the pulses, okay, with a delay in time, because effectively the wavefront is moving at constant speed upwards, but the receiver, with respect to the wavefront, not with respect to the emitter is traveling as well, but I mean, the receiver will receive the wavefronts, okay, with a delay. There is a time delay here. Sorry, delay, or ritardo, delay, right? If the wavefront is traveling upwards and this one is escaping, it will get to the receiver, of course, but with a delay. And if you receive wavefronts or pulses of light with a delay, this means that the frequency here is nu primed. But this guy here, if you have an observer here and another little guy here, 2 physicists, he observes there the emitter and he says, I am emitting with frequency nu. And this guy says, okay, I observe, I receive your waves, but they have frequency nu primed, and of course nu primed is less than nu. If there is a delay, se c'è un ritardo, si intuisce che i tronchi d'onda arrivano lì sempre in ritardo rispetto alla frequenza con cui sono sputati fuori lì. If this acceleration is extreme, se questa accelerazione è estrema, right? If this little guy here says, aspetta che ti mando un flash di luce, ti mando dei pulsi di luce blu. If frequency is less, this is blue, right? If the frequency is much less, it means the color is different. It means the perceived color here can be red. For instance, say shift, appunto, shift. The shift vuol dire, means the variation. So the guy upwards is saying, why did you send to me red light? I wanted blue light. And he says, what happens to you? I am sending to you blue light. And both are right. So this means that in a gravitational field, when an electromagnetic wave is traveling from bottom to top, i.e. from strong gravitational fields to higher levels in the gravitational field, the frequency is changing. It's not compatible. But now Einstein thinks, this is strange. Because here this means that the same thing should happen in a gravitational field on a planet like the Earth. Okay? And by the way, this must be equivalent, uguale. This means that if you send a signal from a lower level to a higher level in the gravitational field, you should observe a red shift, a gravitational shift. And this gravitational red shift, cos'è? What is frequency? Questa roba è un campo gravitazionale. What is frequency? It's, la frequenza, se vi ricordate, è 1 tratto tempo. C'è un tempo, certo, è il periodo tra due massimi. Dunque la frequenza, il reciproco è. Quindi il periodo cambia. Cosa vuol dire che this means that the rate of clocks also, which clocks have frequencies, a periodic. What is a clock? A clock is a periodic phenomenon. It's like a wave. A photon is a clock. Any wave is a sort of clock. This is a clock because it's a simple periodic phenomenon. So if this has a frequency, it has a frequency equal to 1 over the period. The frequency is changing. This means that the time is changing. This means that the time here, the duration t, is of course bigger than the duration up there. This means that the clocks, if you conceive this as a clock close to the surface of the Earth, are slower, because the intervals are longer, than the clocks higher up, further away from here. Clocks here are faster than clocks here. So gravity seems to be something that distorts time. Gravity affects clocks. So it's a new kind of relativity of time. Clocks very close to a planet are different from clocks far from the planet. Okay? Right. Non so quando si fa la pausa.
Adesso.
L'unica cosa interessante dal punto di vista delle vostre ricerche, for your further documentation, this effect, the gravitational redshift predicted by Einstein, has been verified very well experimentally already early on in the 1960s, 1917. I can't remember exactly. But it's a pound-replica experiment done in Harvard University in a tower whose height is roughly 100 meters. And people have been sending intermittent waves from the bottom to the top, and the frequency shift is exactly equal to that predicted by Einstein's theory. Ma non è dove c'è becco. You see how far we are going from Newtonian absolute time and absolute space. Right? After the break, I will show something which has to do with rotating frames.
6 hours later.
You can find many files on the web of this sort of thought experiment. This is about rotating frames. It's very interesting. So rotating frames are non-inertial. Remember that, yeah? If you are on a rotating platform or disc like this, you feel an inertial dragging towards the external walls of the frame system to create a centrifugal effect. Inertial centrifugal effect. And this is then also an accelerated frame because, of course, the velocity is changing direction at each instant time, so this is an accelerated motion. So Einstein thinks that because of the equivalence principle, if you believe, if you consider the equivalence principle as fundamental theory, this means that everything that happens in such a frame is equivalent to what would happen in a corresponding gravitational field. Now, three things in the same experiment can be shown quite well, at least 3 things. Let me start with the time thing again, the thing which have to do with clocks. Okay? Imagine you are in the frame, okay, at rest. Imagine you have 2 or 3 or 4 observers. So this is referring actually to this idea, very simple Einsteinian idea. Clocks on a rotating frame. This is just a picture, right? But this is just telling you that, okay, you have one observer here, very close to the center of the rotation, an intermediate observer here, and one observer at the outer edge. So 3 persons here, one there, one there. Now let's suppose that before the frame starts rotating, they all have their clocks, and they all synchronize their clocks. Yeah? So I have my clock, he has this clock, and your clock. We look at our clocks, and we make sure they indicate the same time. We make sure the clocks work well, and that time is synchronous. So that the clocks is this clock A, okay, clock B, and clock C. Sorry, A, B, and C have synchronized the clocks. What does it mean? It means that at a given instant of time, this clock gives you 3 o'clock, okay? 3 o'clock, okay. 3 o'clock. Okay? And now they say, well, you're going close to the center, because sooner or later this platform is starting to rotate. You are going close to the center here. And B goes there, and C goes there. After a while, we will compare our clocks again, just to see if the clocks are working well. Now, Einstein says, here you have an observer which has a given tangential velocity, right? Rotational tangential velocity. You know that tangential velocity is angular velocity multiplied by the distance to the center, r. This observer rotates with a smaller or greater velocity? Greater, because it's further away. It grows linearly. This one with even greater velocity. It should be linear, of course, with up. Omega is just the angular velocity. It's 2 pi over the rotation. Okay? So if you want a rigid disk, this is a rigidly rotating disk. The consequence which you have to look at, says Einstein, is special relativity instantaneously. That means time dilation. Because it means that t is delta t proper time over the square root of 1 minus b squared over c squared. This means that, conceptually speaking, since the instantaneous velocity of this observer, c, is greater than the velocity of this observer, and is greater than the instantaneous velocity of this observer, this means that his delta t is not equal to this delta t, and it is not equal to this delta t, prime and second. If you change the velocity, if you have a great velocity, given his proper time, the difference will be much, much greater, which means that, effectively, let's imagine that after some time of rotation, if you suppose that for C, you have a clock which is like this, like saying 5 minutes have passed. It's 3:05 on his clock. And this means that B will have a clock which is, esagero un po', which is 3:15. And A, in reality, you have to imagine that this speed here is very, very great. Yeah? Rotating very fast. Okay. But A can be okay. 6 o'clock. So for A, 3 hours have passed. For B, something like 15 minutes. And for C, 5 minutes. And if you would have a very great black hole, if you increase the radius, you would have the limit radius where the speed omega r would be close to the speed of light c, less than the speed of light, because we cannot go at the speed of light. This means that this hypothetical observer, D, his clock, even if D would be synchronized, okay, with A, B, and C, initially, after a while, you can imagine that D goes almost at the speed of light. Semplicemente perché la piattaforma è molto rigida e molto grande. Right? And this means D, his clock, is standing still, almost. It's always 3, maybe 1 second past. So again, the consequence is that in this rotating, accelerating system is equivalent to gravity. This means that gravity, again, affects time. Gravità influenza il tempo. The clock rates. And you see even more. The centrifugal effect here is small with respect to the centrifugal effect here, of course. Yeah? This means that here you are in a weak gravitational field. But here you would be in a stronger gravitational field. So the consequence is, the stronger the gravitational field, the slower the clocks. Più intenso è il campo gravitazionale equivalente, più lento è l'orologio comparativamente a uno nel campo gravitazionale debole, al centro del disco. E corrisponde alla conclusione del ratchet gravitazionale. Okay? You have ratchet if you move away from the planet. La frequenza cambia in questo modo, cioè in modo come si può capire redshift gravitazionale? How can you understand redshift in this image, in this picture? Well, imagine this person here, right? He sees his clock going around as usual, you know. He doesn't feel, his clock is not exhibiting anything special. So, imagine he has a light source, yeah? And he says, I'm going to send towards A a light pulse of a wavefront every second. So, un hertz. Lui vede il suo orologio, he looks at his clock, every second, tac, tac, hai un fronte d'onda, un pulso. Ah. Se hai un impulso ogni secondo per lui, se passa un secondo per D, beh, D va quasi alla luce verde. If you look at A, 1 second of D means 3 hours of A. So that means that the observed frequency by A is extremely low because he will receive one wavefront every 3 hours. Perché qua lo manda ogni secondo. E questo qua ogni 3 ore vede l'impulso. Okay? Relativity of time, I mean, the fact that time slows down here and the fact that the rate of time is not equal here, compared to here, gives you an intuitive explanation of gravitational redshift. Hmm? But there's worse. Now imagine another thing, bending of light rays as well here. Imagine, again, rotating frame. This is the frame in one configuration, right? You have an observer here at O, and he has a light source as well, as usual. And he would like to send a light ray in this direction, a flash of light. So if everything is standing still, no rotation, the light ray would hit the wall of the rotating system here. Now, as soon as, of course, the light ray starts propagating, the frame starts to rotate. We have a frame, sorry. Imagine the light ray just travels along a straight line as well as before. Yeah? Light ray just goes. And however, the frame starts to rotate, so it should be there after a while. This point is rotating with the frame in this direction, right? After some more time, I'm exaggerating for the amplitude of the effect. I mean, just imagine. Light ray has arrived here. Meanwhile, nel frattempo, pointed here. So you have to imagine an observer, of course, here. In Korea, a colleague, okay, was waiting for the light ray of his other colleague. They are communicating with light ray. Light ray propagating. Now his colleague is far away there. So the frame continues to rotate. And in the end, you will have, which is for a very fast rotation, of course. In the end, he will be there somewhere, and the light ray will be here, if there is an edge. So that means that the effective light ray, from his perspective, it has started to go in his direction, but from his perspective, a light ray is completely bent. This is a very fast rotation, of course. This means that in a very strong equivalent gravitational field, you have bending of light rays. Spiego. Il punto dove doveva arrivare si è spostato nella prospettiva di chi non sa di ruotare, e vedi stranamente il raggio di colpire un punto diverso. Dunque, the light ray has been deviated, or you can also use the word deflected. Deflection of light rays. Giusto? There are several ways you can see all this. Big picture. Now you can imagine, you can go back to this little thought experiment about this thought experiment about Einstein. Frame at rest and frame rotating, and we are going to measure length. Distances. You can measure the diameter of this circumference and you can measure the length of the circumference. And how do you measure lengths in physics? Well, with an elementary or fundamental meter rule. An object, a rigid object. So, if the frame is at rest, you can imagine a rotating frame. You can measure the diameter d by taking your elementary meter rule unit and, like you define every procedure in physics, you have to define many procedures. You just see how many times your meter rule fits in the diameter. This gives you d. Then you can work out how many times the meter rule, elementary unit of length, should fit into the circumference. It should obtain a certain length L. And of course, if the meter rule is small enough, and if you do the measurement correctly enough, you should tend to L over D, you should tend to pi. L over D is always pi. Now, imagine that you have a rotating frame which is rotating. And here Einstein tells again. If the frame would be rotating, you would have every elementary unit meter rule, unit of length. Every elementary unit of length must be affected by the length contraction. I've been speaking about time dilation before, but you know about length contraction. Length contraction happens in the direction, instantaneous direction in this case, in the direction of motion. This means that you have length contraction. So here you should have L naught, so to speak. But I mean, roughly speaking, okay, L is L naught times relativistic factor. So if you have a speed v which is great enough, the length of your meter rule, I don't know, you can see it here, undergoes length contraction. It is smaller than the meter rule at rest. This means that there are more meter rules that fit into the circumference than before. On the other hand, the meter rules which are along the diameter, they do not undergo length contraction in their length, but only in the width. that doesn't matter. You understand? The piece of length here is moving like this. So length contraction happens in the direction of the width, not in the direction of the length of the elementary meter. So the diameter remains the same as before, sorry. But the length is not the same anymore. It's an L primed.
Posso farti una domanda?
Yes.
E questo ragionamento è per un osservatore esterno, capisco bene? Però per quello che si trova sul bordo vale sempre il rapporto LCD.
E quando l'osservatore esterno e quello interno, quando fanno il confronto, c'è una...
Ok, ma quindi se uno proprio si trova sul bordo, per lui continua a valere LCD uguale a Y, giusto? Sì, ok, no, adesso certo.
E come la contrazione per avere la contrazione delle lunghezze? No? And so, effectively, for the moving system, you would have not the same result because L primed is bigger than L. Is different. But this is bigger or greater than time. So the diameter is not changing, but the effective measurement of the length of the circumference, that would be changing. If the circumference is rotating, if you perceive rotation. And this means, this is one of the first ideas that Albert Einstein had that brought him to non-Euclidean geometry. This is consistent with flat Euclidean geometry. Okay, Euclidean geometry. This is consistent with non-Euclidean geometry. Now, I was thinking about a version of that in order to answer your question in a clear way, which is compatible with this idea. Imagine one rotating frame. Okay? And again, two observers on the same rotating platform, one here and one there. Now, these two observers have a relative speed. That means that if one observer compares if observer A does the job and observer B does the job, when they compare their results, okay, he has a certain value of L over D, he will have an L primed over D. So these two results cannot be the same because if he looks at his result and if he looks at his result, there is a relative speed, c'è una velocità relativa, dunque anche se sono entrambi sul disco, vedono, quando confrontano i loro risultati, vedono un risultato diverso, non può essere lo stesso. E Einstein dice, in a weak gravitational field, okay, you have an almost Euclidean result. Space is Euclidean. In a strong gravitational field, the geometry of space is not Euclidean. E qui abbiamo un capitolo enorme, cioè la geometria non è euclidea, non-Euclidean geometry, and the role of non-Euclidean geometry in general relativity. Okay? This is one of the first intuitions of Albert Einstein that brought him to the idea, well, here we have something which might have to do with non-Euclidean geometry. Yes? So let's summarize a few conclusions we have out of this. first one is that gravity. Gravity must deflect light rays. Gravity must produce gravitational redshift, affect clocks, and generate redshift. Gravity has to do with non-Euclidean geometry, distortion of geometry. Strange, huh? So, capite, cioè, you understand? Roughly speaking, Einstein's intuition is that gravity distorts Minkowski spacetime in the end. You see, if this is the old Minkowski spacetime metric that we saw last time, the fact that you affect clocks and time intervals, this means that this, if there is gravity in this space-time, yes, then something must happen here. There must be a factor here, which depends on the gravitational field. But also, if you believe that gravity distorts space in order to generate non-Euclidean geometry, then it should also be present there in order to distort geometry and generate curved non-Euclidean space. And all these 3 or 4 factors, they should all be related to gravity, to some kind of gravitational potential. Now, let me explain to you slowly, this is the last thing, how more precisely Einstein is going to understand that gravity has to do with non-Euclidean geometry, with non-Euclidean space, apart from all these effects. Can I erase this? Any questions? This is what is usually called Einstein's happiest thought in life. It is the following idea. It's all related to the equivalence principle, but it's very fundamental. It's simply saying that a freely falling observer, I'll write it down first. Freely falling observer experiences weightlessness, experiences no gravity. No gravity. Capite questa cosa? Un osservatore, cioè un corpo, un osservatore in particolare, che cade liberamente, okay, in un campo gravitazionale e non sente nessun campo gravitazionale. Lui. Immaginate di essere immaginate di essere in un sistema di riferimento, in un campo gravitazionale, sulla Terra, in un sole, in una pratica, in qualche parte, sospeso. E se qualcuno taglia la corda, cadete liberamente. Cosa sentite nel sistema vostro se cadete liberamente? Assenza di gravità, quella sensazione è l'assenza vera e propria di gravità. Okay? Equivalence principle. The equivalence principle is fundamental, of course, here. Qualcuno che cade liberamente, someone was freely fall. If he has with him other objects, for instance, a piece of chalk, a pen, a handkerchief, paper, rubber, all these things, because of the equivalence principle, all these things fall with the same acceleration g we had been mentioning earlier on. And so, from the perspective of this local observer, I will insist more on this complicated term, local observer. From the perspective of this local observer who's freely falling, if he can't look outside, he will say, I am in a zero gravitational field. There is no gravity. Yeah? Why do I say local? Localmente un osservatore in un sistema, un osservatore in caduta libera sperimenta effettivamente l'assenza di campo gravitazionale. Questa domanda, in realtà, this is a question which is indeed very important in my own view. It is extremely important. You know, in physics you have to be very clear when you define variables of a theory. These variables, these quantities, they must not just be quantities, they must be measurable. They must be observable. In particular, you would like to define observables in an absolute way, right? Universal observables. Now, if you ask someone the concrete question, what is a universal observable? For the gravitational field. Qual è l'osservabile universale della gravità? Vale a dire, i.e. this means, how can I be sure to observe gravity somewhere? Domani, in quest'aula, siamo tutti italiani, in quest'aula c'è la gravità? Si dice sì. Com'è che lo sapete? Come? È attaccato alla sedia? Sicuri? Si può alzare però. Cioè, com'è che vedi la gravità nell'aula? Com'è che vedi che c'è la gravità? Beh, dici semplicemente, prendo il gesso, mollo, cade. Dunque c'è presumibilmente la gravità. Cioè il moto di caduta sembra essere l'osservabile, diciamo, universale. In realtà non è così, appunto a causa di questo principio di equivalenza, che rende le cose in realtà molto complicate. Perché? Perché il fatto che potete semplicemente dire guardo e vedo le cose cadere qui, dunque qua c'è la gravità, ok, in parte probabilmente è giusto, ma è dovuto a una nostra situazione molto privilegiata nell'universo. sotto i nostri piedi abbiamo un suolo rigido. Grande privilegio. In che senso? Tu sei fermo a causa del suolo rigido e l'oggetto accanto a te no. E c'è un moto relativo tra i due. Ma ricordate la situazione generica, cioè normale nell'universo. L'universo, queste miliardi di galassie distribuite su questi filamenti cosmici, la situazione normale dell'universo è normale, cioè una situazione molto probabile di essere nell'universo non in questa situazione estremamente privilegiata, ma persi in un vuoto cosmico. Apparentemente vuoto cosmico. Una di queste cellule gigantesche di vuoto cosmico che misurano centinaia di milioni di parsec. Se sei lì da solo con una sola e ti chiedono dimmi qua se c'è un campo di gravità. Non sei più coi piedi sul tuo suolo rigido, privilegiato. E anche se ci fosse un campo di gravità, a causa del principio di equivalenza, tu potresti tirare fuori il fazzoletto, le chiavi della macchina e lasciarli cadere, lasciarli mollare accanto a te. Tutti quanti, a causa del principio di equivalenza, hanno la medesima accelerazione gravitazionale. Dunque non c'è nessun moto relativo tra te e qualsiasi altro oggetto. Quindi non è più un osservabile universale questo. Però ce n'è uno. E questo si chiama, in inglese, Relative Acceleration or Tidal Effects of Gravitation. Relative Acceleration or linked to Tidal Effects. E questa è la vera gravità. Non sono le cose che calano, questa è una situazione privilegiata. Nel senso che, e qui emerge il significato della parola local. Locale, local. Dunque immaginate che siete persi in questo vuoto cosmico. Vabbè. Immaginate che però avete, non so, per prendere un esempio, una busta con delle mele, un sacco di mele, di patate, e mettete le mele nello spazio intorno a voi in forma circolare. Intanto siete nel vuoto, restano lì apparentemente, anello circolare. E voi là in mezzo. Sempre nel vuoto cosmico, andate stendendo. E quello che succede è evidentemente che, ok, se siete, voi non lo sapete, ma c'è una massa oscura che genera un campo gravità. Guardate cosa fanno le mele. Tutte quante cadono, vuol dire accelerano, verso la massa, la distribuzione di massa. Però guardate cosa succede, questa mela rispetto a questa qua è più vicina. Qui l'accelerazione gravitazionale di questa è, esagero la differenza, è un po' maggiore dell'accelerazione gravitazionale di qua. Ad esempio distante la G cambia. Ma non solo, questa mela, cioè tutte le mele, guardate, la direzione del centro di questo corpo è questo qua. Il modo di tutti i corpi, compreso il vostro, è diretto verso il centro. Così. Dunque, man mano che questo anello di mele cade insieme a voi, la sua forma si deforma, appunto, nel senso si cambia. Perché queste mele qua cadono più veloce, quella resta un po' indietro perché l'accelerazione è minore, intorno a te vedi, e allora, vedete cosa succede? Le mele esterne si ravvicinano, dunque accelerano l'una relativamente all'altra, anche questa relativamente a questa in un altro modo. Relative acceleration. effetto di marea, di distorsione di marea, è quello. Quando cadete, effettivamente le mele saranno messe dopo tanto tempo, non lungo la circonferenza, ma lungo un'ellisse. Mela in giù, mela in su, mela a destra, mela a sinistra. Tra le due c'è sempre una accelerazione relativa, cioè la differenza vettoriale nello spazio tra l'accelerazione di questa mela, l'accelerazione di questa mela e questa non è mai nulla. E questo indipendente dal principio di equivalenza o no? Quindi se tu vedi una roba del genere succedere da qualche parte nell'universo, puoi con sicurezza universale concludere sono in un campo gravitazionale. Questa è la vera misurabile fisica della gravità. Capito? Ed è un effetto non locale, e localmente attorno a te questi effetti sono minimi, come vedete, no? Dovete guardare su distanze un po' più grandi dove gli effetti sono amplificati di questa, eccola qua, non uniformity, non uniformità, non uniformity of the gravitational field. Chiara sta roba?
Sì.
Che due punti diversi del campo gravitazionale hanno accelerazioni gravitazionali distinte e questo ha effetti misurabili, assolutamente. Non hai bisogno di avere i piedi da qualche parte su un suolo rigido, puoi anche essere perso da qualche parte e cadere. E this is what I mean. The non-uniformity of the gravitational field is a universal observable for the gravitational field. This is really what gravity is about, okay? Physically. And tidal effects, gli effetti di marea che la Luna crea per esempio sul nostro pianeta, li conoscete bene, and you have the Earth, right? Sorry, Earth, and you have something like the Moon. What happens? The Earth is really falling together with the Moon, okay, in the gravitational field of the Moon. This means that the points here have a greater gravitational attraction towards the Moon than the points here. And so forth. And these are accelerating in a different direction. These are accelerating in a different direction. Accelerating in a different direction. So if you pull here and you pull there with another acceleration, the net effect is a sort of elastic deformation. And the Earth, of course, not so much the solid part, the liquid part of the Earth, distorts itself exactly equal to the way the apples distort their shape and generate an elliptic distribution, not a circular distribution. So the Earth distorts itself and has this shape, not a perfectly spherical shape, because of the non-uniformity, because of the differential relative acceleration effect in the gravitational field generated by the Earth-Moon system, rigorously speaking. This is a true reason. And these are non-local effects. Okay, you have to look at effects at great distances. Okay? Quando mi dicono che i capelli sulla testa, che queste cose che dicono che la Luna ha degli effetti sul corpo umano, quindi bisogna tagliare i capelli quando va su e cioè un corpo umano, il diametro della Terra sono 12.800 km. Okay? È quella che si sente la differenza gravitazionale tra qua e tra questo punto. Il corpo umano è un metro, va. Quindi la differenza gravitazionale tra testa e piedi non è nulla, è minima, semplicemente perché la distanza tra la testa e il piede è dell'ordine del metro per un essere umano normale. La Terra è un po' più grande e sente ovviamente questa differenza, che il campo gravitazionale è non uniforme, okay? Quindi non c'è nessun effetto della Luna sulla crescita dell'insalata. Ma comunque è importante. Let's go back to Einstein. What I'm saying now is a starting step for next lecture after Easter. He's saying that locally, ecco la precisazione, locally, a freely falling observer experiences no gravity. Se guardi localmente non vedi la gravità se cadi libera, se il sistema è in caduta libera. Freely falling vuol dire cadere libero. L'intuizione geniale di Einstein a questo punto di dire, guarda, se localmente non c'è gravità, vuol dire che localmente, nello spazio-tempo, la metrica, lo spazio-tempo può essere approssimato dalla metrica di Minkowski, piatta, non curva. Questo è geniale. Locally, space-time can be approximated by flat Minkowski space. È come dire, pensate a una sfera che è anche non euclidea, la sfera, no? Vi lascio andare. La sfera è anche curva, la sfera non è euclidea la superficie di S2. Ok? Ah, c'è la geometria. Localmente la sfera sembra piatta, localmente il nostro pianeta sembra piatto. Dunque localmente sulla sfera puoi utilizzare la metrica, la geometria di un piano. Cosa che quando vai da un posto a un altro luogo, il piano è sempre un piano, però non è lo stesso piano. Le coordinate che utilizzi qui, nello spazio, le coordinate che utilizzi qui, ovviamente non sono equivalenti. Quindi se cambi le coordinate per essere in ogni punto dello spazio-tempo comunque in uno spazio di Minkowski, vuol dire che sono le coordinate che si incurvano e quindi che lo spazio-tempo è curvo quando c'è la gravità. È geniale. Che localmente non sento la gravità, localmente non sento la curvatura. Ed è straordinaria. Quindi Einstein arriva a dire che ciò che noi chiamiamo gravità non c'entra niente con una forza. It's not a force. It is a manifestation of the fact that space-time is non-flat, is curved. Geometry is non-Euclidean. And you can even understand that when light travels from this point to this point, it's not a straight line. It is a circle arc. It's curved. But it is curved not because there's a force. It's curved because geometry is curved. Space is just non-Euclidean around massive objects. So this is the intuition which I will develop after Easter. Right? Have a good Easter time. Bye.